All right. So, talking about state machines, Kotlin, coroutines, and some other stuff that I'm interested in. So I think I just want to show you like a quick agenda. So I'll talk about what is this talk, what is the point of it, why, a bit about finite state machines, about Kotlin, coroutines, scope, context, all this stuff, flows, channels, finally state flow, and then I'll show you one opinionated implementation of something that seems like a state machine in Kotlin with all of this tech that I mentioned before. So we'll go through language and symbols, implementation details, DSL, and state and error handling. All right, so let's move on. What is the talk about actually, and why am I doing it? So there are multiple reasons. I like playing around with new technology, primarily, but there are some more serious reasons. I like seeing old problems being solved in a new way, maybe in an easier way, and also some new problems that were previously difficult to solve. Now they might be super easy to solve with the new technology. So these are like the more serious reasons. And then I also want to showcase some of Kotlin's asynchronous tools and inspire maybe some of you to look into them and write new libraries and solutions. So that would be kind of my motivation. So I hope you're ready. Let's jump into it. So finite state machines. As you might know, there are lots of different state machines. I'm focusing on finite state machines in particular because they are probably the easiest, and they are a really good example to showcase what I'm trying to show. They're usually used in vending machines, in gate entrances, in the subway. They're used in heating systems, self-driving cars, many software frameworks, particularly in the UI frameworks, on mobile especially. I have a lot of background in mobile, so I kind of come from that world, and the problems that I would like to solve in an easier way are usually software frameworks. So this is like the most basic use case of a state machine, which is a turnstile. You know it from subways, and this is what the diagram looks like. So it's basically just two states, locked and unlocked, and there are two actions: inserting a coin and pushing the metal rail. And so it's quite simple. So we call the states just states. The white dot marks the initial state or the first state, and then we have inputs or actions. So people call them differently. I think throughout this presentation I will use the words input and action interchangeably. So I'm referring to things that you give to the state machine to try to trigger a change inside of it. So that's like the basic use case for a state machine. And now I want to jump into like more interesting or more serious topics like Kotlin and coroutines. So we use maybe like a quick show of hands who is writing Kotlin or who knows Kotlin. Okay, so some of you. Right, so I'll try to be faster because you probably are familiar with the coroutines. So basically we use them for background work and for threading mostly. It's an asynchronous programming concept or an asynchronous programming framework, and they kind of make asynchronous code look synchronous. Unless you're using IntelliJ or Android Studio, then you get icons on the side, so it's very obvious when the code is synchronous and when it's asynchronous. And maybe, possibly, it's making developers happy or happier, if developers can be happy at all. So launching coroutines, it's the basic use case. You just use the launch function and you open a Lambda. If you're coming from another background, it's also called closure. or a higher order function, but in Kotlin we call it a lambda. So we just launch a function and it executes something here. It's easy to switch threads using a function that is something like this with context, and you give it which threads to run on, and then you do something important like get user profile from the repository, and what you get is a result. So it looks synchronous, but in reality, the compiler is smart enough to like change the code around, and this is basically asynchronous code, this line here. You can also do try catch and stuff, and finally you can cancel your jobs. Something you get from the launch function is a job, and then you just cancel it. So it seems pretty straightforward. Internally, it's super complex, but yeah, not trying to focus on the inner workings of coroutines, just to kind of showcase what they can do, so we can move on to more complex topics. I've showed this diagram in other talks before. It's one of my favorite diagrams because it's complicated, but not as complicated as JetBrains blog posts. So it kind of simplifies what they were trying to convey. I just want to go quickly through it to convey the meaning of scope, coroutine scope, and coroutine context. So just simply put context here and this one here. It's basically a collection. It's basically a configuration for the coroutine and how the coroutine will run and what the coroutine is all about. And it can contain stuff like job, dispatcher, exception handler, other things, name. You can put many different elements inside of the context. So it's basically the configuration of how the coroutine will run. And if you launch a new coroutine, you need to do it from a coroutine scope. So scope is basically a wrapper around the context, and it does nothing else really. So it just holds the context. It's just an interface with one property, which is the coroutine context. So you cannot use functions if you are not. You cannot use the coroutine functions like launch if you are not in a scope. There are workarounds. You can do some stuff to hack it, but normally idiomatic Kotlin code requires you to be in a coroutine scope. And to be in a coroutine scope, you basically just implement a context. So in this case, we can imagine that we have some kind of parent job, which is managing all of the child coroutines. We have a dispatcher in the context, which is kind of telling the coroutines where to run, on which threads to run. And we have an exception handler, which will handle all of the errors that happen in the parent coroutine or in the child coroutines. And then when we call launch up there, we can also provide additional context, which is basically just a collection. And then this context gets merged with the parent context in order to create the child context. So it's kind of complicated, but the coroutines internally deal with a lot of complexity. So you don't really need to think about it a lot. You just say launch and open a lambda, create a function, and all of this will kind of get crunched together into a context for your new coroutine. And so JetBrains has written a lot of code internally to handle child-parent communication, errors on the child side, finishing coroutines on the child side, and you don't really worry about that a lot. So just to recap on the coroutines, basically the scope is the wrapper around the context. Context is a collection of elements where each coroutine element, context element, describes some behavior of the coroutine that you're running. So it's kind of a configuration. There are several words, several terms that we use. A job is basically your controller for the coroutine. You can cancel the job. You can wait until it completes. You get it, for example, from the launch function. There's a parent job for all coroutines that run from a coroutine scope. And you can handle child coroutines easily if, for example, if you use a supervisor job, because then supervisor job gives you access to child coroutines. It gives you some other superpowers, like if your child coroutine fails or throws an exception, it will not fail your parent job. Whereas with the standard parent job, any error in child coroutines will also throw an error to the parent. So there are these terms that might be important. There's a concept of a suspending function, and basically it's just a function where we put a suspend keyword in front, notifying the compiler that this function might take a while to complete and might go away to another coroutine or might go away to another dispatcher, to another context to complete. So we're kind of telling the compiler that there is something that might take a while or take a break inside of the function. And exception handlers, where we put a function that handles exceptions, and if you put it in a coroutine scope inside of the coroutine context, then the function will handle all of the errors from within that context. There is a hack function that a lot of people use online. I actually don't like using it because it's confusing and it's also misleading in many ways. It's called run blocking. It kind of allows you to merge the synchronous and asynchronous worlds. And once you open the Lambda after run blocking, the internal of that Lambda is a coroutine scope, which you can use. But the external run blocking function is not a coroutine scope. And it will block the thread that is calling run blocking. I don't like it because it's kind of misleading. It's telling you that you can run something asynchronously, but in fact you can't. It's basically blocking you at the place where you call run blocking. So I'm kind of trying to avoid this function in general. Okay, so moving on to flows and channels. So with coroutines, they give us the ability to run asynchronous jobs on different threads. They give us the ability to branch out and do maybe multiple jobs at the same time and possibly merge them together. But flows and channels are not async primitives as coroutines are. They're more complex and they're like one level above. And they allow us to process things in a producer-consumer fashion. And they allow us to process things something like this, where you would create a new flow and you would emit items into that flow. And once you are inside of a coroutine, then you can call collect. And then all of your items that are emitted in the flow, they would all get emitted, printed on the screen because of this collector. So flows allow that, and channels initially were meant for communication between different coroutines, but at some point the thing grew, and they now do much more. There are many types of channels, but I'll show you some of the more interesting ones. But basically, they are like let's say a message queue, kind of, where you send stuff into the channel, and somebody else is listening to the channel, but the channels are kind of live. So flows are set up, let's say, statically, and channels are live. So at any point you can push stuff into the channels, whereas with flows, they're not live concepts. So yeah, we say for flows, we say that they are cold because they don't take any resources from the system before somebody calls collect on them. And we say that channels are hot because they are live, and as soon as you create a channel, it starts consuming some memory, it starts consuming some CPU. Of course, it's like suspended and waiting, but still it consumes some memory. So flows are like for static stuff that you know already and predefined stuff, and channels are for live stuff. Also, there is one behavioral difference as well. In flows, when you subscribe with different consumers, the flows will not duplicate events for for different consumers. So each consumer would get the next event, and somebody might miss out on events. Whereas with channels, that doesn't have to be the case, because there is like a special type of channel, a broadcast channel, where you can broadcast to everyone listening. So there's like a slight difference, and I'm mentioning this because it matters for the next thing I want to talk about. But more importantly, both flows and channels require a coroutine scope if you want to listen to the events that go inside. And in case of channel, you also need a coroutine scope to shoot events into the channel. There are many operators, like map, conflate, zip, delay on each. It's very similar to the collections API, and they allow, it's all written by JetBrains, it's all in the same library, and they allow you to use channels and flows as if they are as if they are collections, and not like asynchronous, let's say, streams. They're not really streams, but yeah, very similar. Maybe out of curiosity, who knows what conflate does, or what conflate means? Okay, not many. So imagine you have a producer that shoots thousands of events, but you have a consumer which does something with each event that is super complex and super slow. And there would be a lot of events stuck in the queue, and the producer would kind of, it would shoot events until there is no more memory, but the consumer would not get events until it processes the previous event. And so it's kind of starving the consumer. So if you call conflate, that stops happening at the cost. And basically what happens internally is that the producer can still shoot events, but the consumer gets only the last event. So all of the events get dropped, and the consumer only gets the last event. So conflating means basically just drop everything until the consumer is ready to process. And that's actually an important one. That's why I was emphasizing it. Yeah, and flow and channel in general, people compare it with stuff that comes from the Reactor framework, ReactiveX, live data. I forgot to mention here, but it's also very similar to promises in some way, if you're coming from the JS world. And there are also some similarities with optionals in Java 8, but it's quite different because it works with the coroutine with the coroutine framework, and the coroutine framework is somehow built into the language, so it's slightly different, but it's comparable somehow. And there are many functions that can convert between flow and channel and reactor or ReactiveX or live data or promises. So it's like bidirectional. You can convert from one to another. So why I was mentioning conflation and why I was mentioning hot and cold and all of this stuff is it's kind of old already in the tech world. It's like a year and a half old or something. But it's called state flow. And a state flow is an exception to the rule. It's a hot flow. So flows are usually cold and static, and this one is hot and it's live. So you can change it, and it would trigger events. It would allow you to do something like this. So you would create a mutable state flow with an initial value, let's say 0, and then you would expose a property externally to other users. You could just say as state flow, and that would expose a property that is read-only. And if somebody calls increment, you would go to your mutable counter and call update. You would get the current value, and you can also put a new value that is based on the current value. This is important because you don't have to think about thread safety at this point. So this update function will take care of everything, and all of these lambdas that go inside, they are ordered, and also the order execution is guaranteed that it will be thread safe by the framework. So yeah, that's what is interesting. You can somehow mutate a value in the state flow, and without any consequences. And people can other people who are building on top of what you built can listen to the state flow and get notified about the changes. So some of the main properties, it's a type of shared flow, and shared flow is a hot flow, as I mentioned. It's like an exception to all of the flows, and all collectors will get all values, so it behaves like a broadcast, which is different from the flow normally, because normally flow would not notify everyone, but this one does, and so it's kind of different. And then it exposes a single updatable value where you can call update, as I've shown you in the example. And it has a read-only state API. So you would use something like this if you are building something internally, and then you want to expose it to others, but you don't want others to modify your code. So read-only state API and a value property, which is super important because no other streaming. Well, in ReactiveX there is behavioral subject. If you're familiar with ReactiveX, then with behavioral subject you also get like a last value plus all of the updates, and that's what the value property does in the state flow. And it's conflated. That's why I was asking earlier. So it basically ignores the slow collectors, and it will only emit the last value to the collectors who are ready to process. This has an interesting consequence. If you have 5 collectors, 4 of which are super slow and 1 is super fast, the super fast one will get all of the updates, but the 4 slow collectors will not get all of the updates. So that's an interesting consequence of being conflated and being a shared hot flow. Okay, so there was a lot of ins and outs of how coroutines work, how state flow works, and I have an implementation of a finite state machine, which I was playing around with. But first, I want to say a disclaimer. I'm not saying that this implementation is a great or a good implementation, and I'm not saying that you should use it in production, and I'm not saying that it's safe to use, although I wrote a bunch of tests for it, and it seems like it's working. I've tested a bunch of things. So also, it's important to know that this implementation, it's like my opinionated implementation, and some of the decisions I made are based on my previous experience. It's not aiming to solve all of the problems, it's just kind of aiming to solve the base problems, and I plan to build on top of the base I have here. Okay, so let's go into language and symbols of the implementation. So for actions, or inputs, or signals, depending on what you want to call them, I call them actions. I thought it would be nice to have an interface and to have a name for each action internally, and also a payload. I've been told before that the payload was a bad idea, and I tend to agree, but since I didn't change it yet on GitHub, I'm keeping it like this. Although I believe I will remove the payload in the future. Anyway, it's not used anywhere throughout the presentation, so it doesn't matter. But just for the people who want to give feedback that the payload is not a good idea, I understand. I agree. I'll remove it later. Same thing for the state. It's basically just an interface. It has a name, and it has the payload, unfortunately. So going further, a transition, I define it as like a record or a data class in Kotlin, or some would use also vector. So it's basically just 3 things: the old state, the action, and the new state. It's quite straightforward. It's used for telling other people who are listening to the state machine or using the state machine what happened. So something went from the old state to the new state, and why it happened, because of the action. State mapping is an internal class that I use to create mappings from one state to another, and it's very, very similar to the transition. So it has a source, it has a destination, and it has an action. And these are all the same types internally, so almost no difference. And I want to show you the interface. So what I could do is, now I could create a val, just a read-only property, which would contain the current state. I would also have a read-only property that would contain the last action that happened on the state machine. For debugging purposes, I have get all states and get all actions. And then maybe one of the more important things, adding a state mapping here, where I'm just adding a new state mapping data object. It basically contains source, destination, and action. So in the turnstile example, it would be unlocked, it would be locked, coin, unlocked, basically. This mapping would say source is the locked state, action is the coin, and then unlocked would be the destination state. So that's the mapping. And to set up the state machine, you need to call these for a number of states that you have, a number of actions. And then the initial state, if you fail to set the initial state, currently I crash everything. And I believe that makes sense because you need an initial state in a finite state machine. Then going on, transitions. Transitions, it's a flow which you can subscribe to. You actually don't know that it's a state flow externally, but it is a state flow internally. And then you get transitions from it. So if you subscribe to transitions, you start collecting events from them. Then you would get these objects which contain data about what happened, which state was the old state, which state is the new state, and the action. It's identical for the arrows, so it's also a flow. Internally, it's also a state flow, and it just emits throwables. And finally, the transition function, it's used to call the state machine and tell it to move into another state. And because you don't know which state it will move to, you are only providing an action here. So you provide an action, and then it moves to a new state. Because this is Kotlin, and this is coroutines, and this is the coroutine scope, and so on, from the transition function, I return a job so that you can cancel your transition. Sometimes the transition can take a while, and you're maybe on a mobile device, and the user swiped to close the app. In that case, you don't want to keep the job running in the background, but instead you want to close or stop the job completely. So that's why you get a job instance, and you can call cancel on it. And then the last function is the finish function, which is kind of a cleanup function. It closes all of the dispatchers internally. It stops all child coroutines. It stops all transitions, and pretty much stops everything. And then you cannot use the state machine anymore. So I also want to show you some implementation details internally. And basically, we start with the coroutine scope and the coroutine context. So as I mentioned before, if you want to run child coroutines anywhere, you need a coroutine scope. So my state machine, in this case, is extending the coroutine scope. And what I'm forced to override is this property, coroutine context. Basically, the coroutine, the context elements that I use here are the parent job, which is a supervisor job, because I also want to control the child coroutines. And also, if one of the child coroutines fails, I don't want to fail the parent job. So I'm using a supervisor job there. I'm using an exception handler. Of course, I didn't put all of the code here, so there's just a comment. And I'm using the exception handler function. This is actually a function. This one, coroutine exception handler. It comes from the coroutine toolbox, and it creates a new handler. Both of these are coroutine context elements, and their type allows me to use the plus operator here. So if I had more of these elements, I could just plus them on top of each other, and the end result would be a coroutine context. So that's how we set up the coroutine scope. Then the next thing is the mutable state flow, probably the most important part or the most interesting part. And this one is mutable, so I keep it private. Internally, so I create a mutable state flow. I create a transition, and this is the initial transition. It goes from none, which is a predefined state, and it goes through birth action, and it goes to incubating new state. And the reason why I have this is, well, it's a twofold kind of thing. Why I have the incubating state. One is because I'm expecting the user of the state machine to add state mappings inside. I'm expecting the user to add like all of the states, all of the actions, and how they map together. And also, mutable state flow requires a default value. Without a default value, you cannot construct a mutable state flow. So it's kind of a two-part reason, but it makes sense because then it's easier also for me to figure out if people are using transitions before they've actually set up the state machine. And then in that case, I explode everything. And to expose to external users, I have this transitions property, and it's a flow of transitions. And it's basically just this same mutable state flow, but I'm hiding the type of the flow by using an interface there. So that would be how externals can access the transitions inside of the state machine. And then it's kind of identical for error flow. It's a mutable state flow. It just emits throwables. And again, for the reason of mutable state flow requiring a default value, I'm throwing an incubation exception. It's not really being thrown because you could skip it. And I'm pretty sure that I should have skipped that one here. So you can just call. I'll show you. There's a slide with that. But you can just drop any number of events from any flow by just calling drop. And yeah, I'm exposing externally just a flow that emits throwables. So basically, as a user of this state machine, you can listen to transitions, and you can listen to errors if you're interested. Okay, so that was the setup of the state machine. I also want to show you the kind of implementation. I guess the most interesting one would be transition function. So this top part is important because I am setting up the coroutine, and so this transition function returns a job, as I mentioned. As soon as this is called, I'm launching a new coroutine in there, and there's nothing else really going out of this function. It's just a job. So everything that happens inside of the transition function is in a coroutine that can be moved to any thread, and it's happening kind of in the background. Well, if you choose to run it in the background. Similarly to threads, in JVM and probably in many other languages, you cannot just stop them or drop them at any point you want. You need to call stop, suspend, whatever, cancel depending on the API you're using. And coroutines are very similar to that. You cannot just stop a coroutine if you call cancel. It will not cancel automatically, magically. You need to think about that when you're writing code that is asynchronous in coroutines. And that's actually what this line 6 is about. So I'm asking if it's not active, just return. And that's because I don't want to run the whole function if somebody called canceled. And I'm running this check multiple times. So I have it here, I have it here. I omitted a lot of code there, which was not interesting, but I have it in many places. Basically, before any important action, I'm checking if the coroutine was canceled, and then just returning, getting out of it. So that's kind of setting up the async part, and the transition after calling launch, this transition becomes asynchronous. And the user of the transition function just continues doing whatever they were doing, and they can listen for transitions or errors depending on what happens. So how do I decide what happens next? Basically, I'm going through the state mappings. I have it's like a dictionary or a collection of all of the states, all of the actions, and how they map together. And I'm going through these mappings and looking for a candidate. So somebody said, run this action. So the argument to the function, somebody said, run this action. So I'm trying to find a state mapping where the current state and the given action result in something. And if I do find it, it's pretty straightforward. So I just create a new transition. Old state is the current state. Action is the one that was provided as the argument to the function. And the new state is coming from the mapping that I found. It's the destination. And then just updating the value is super easy. I just call the transition flow. This is the mutable one, the private one. I set the value to this transition. Setting the value here also internally triggers the state flow to notify all of the collectors, all of the consumers. So this is like the main thing that happens. So I just put it in the flow, set the value synchronously, and then it will notify all of the consumers, and the consumers are all inside of their own coroutines. So if they decide to process something for a very long time, they can choose to do so, but it's not blocking this code, and it's not blocking, consumers are not blocking each other in any way, and they're not stealing events from each other in any way. And that would be the happy case where I found a mapping, I notified the flow, and it's out. The sad path would be basically the mapping was not found, so this question mark dot let is a null safe operator, and the mapping was not found. So therefore, I need to emit an error, and the error is a no mapping exception. I also give the current state and the action to the flow, and so somebody who is interested in listening to these errors, they know what happened. They know which state triggered the error, and they know which action triggered the error. So that would be, I guess, the most interesting part. Do I have, is this time correct? How much time do I have? Okay, so maybe something interesting that Kotlin can do is create domain-specific languages, or DSLs. And I want to show you what I did for creating the state machines. And basically, it looks something like this. I'm using a sealed class, water action. So it's extending a singleton action. This is just has a name of the class. It doesn't do anything special. And then there are 4 different types of water actions. And what can you do to a water in a glass? You can heat it, chill it, drink it, or fill the glass. And similarly to that, I have 4 states of water in a glass. It's ice, steam, liquid, and like empty glass. And so since all of these are objects, I can just use them using that name. No constructor needed. Nothing is needed, really. So how do I create a state machine? And this is the fancy part that Kotlin allows. I created a bunch of code around it so that it could look this way. But like this is an infix function, and this is an infix function here as well. And this is a mapping function, and it would look something like this. So you just open a state machine, and then you say heat moves ice to liquid, and you would define it that way. It's, I don't know, it cannot be easier. And you define all of your states, you define all of your actions, and finally you can just say initial state is empty. So an example how you would use the state machine in this with this API is the transitions job equals launch, and you can choose your own dispatcher. It's probably a good idea to use a single thread dispatcher because you don't want your events to come on different threads and then be handled in a wrong order. So it's probably a good idea to have a custom dispatcher here. And so it's kind of straightforward. You just take the state machine, take the transitions flow. I'm dropping 1 because I want to ignore the empty state. And then you call collect. Whatever is in the collect lambda will process your transitions. For errors, it's pretty much the same. You just launch a coroutine. Inside of it, you say state machine.errors. You get the flow. Whether you want to drop 1 or not, I don't know, probably yes. The incubation error should be ignored. And then you collect with a lambda. You can do whatever you want. It just gives you all of the errors. So the API is probably very straightforward, probably not interesting. The transitions call is something that might seem confusing at first, but it kind of makes sense. So what I do here is I call transition by default. There's a fly. So by default, the state machine that I built is in the empty state, like it's an empty glass of water. And then I say fill. I just transition using the action fill, and it goes to liquid. And then if I call it again with chill, it goes to ice. And if I try to drink it, I send the action drink. This one will not succeed because there is no mapping from ice using the drink action to anything. You can drink only liquids. So this one would fail. And then you can heat it. So you call transition with heat, and it would go back to liquid. And finally, you can now call drink because now there is a mapping from liquid using drink, and it goes to empty. And the weird thing here is that you call these transitions, and some of them might take time. So in this example, they won't. But in reality, some transitions will take time, and they will be complex, and they will be slow. So that's why all of them are coroutine jobs. So you run a transition, and you need to wait for it to complete. So I'm keeping references to all of these jobs. And then what I can do, for example, is make a collection of all of these jobs, and then say join all. This basically blocks the execution here until all of the jobs are complete. There are better ways to do it. If you are in a coroutine scope, you can just launch new coroutines without any issues. If you are in a coroutine scope, just calling this transition will launch a child coroutine, and you would be able to go to the parent scope and say parent, cancel all children. So there are better ways to do it, but I wanted to illustrate what happens behind the scenes. So if you don't do this line, and if you let them complete on their own, it might happen that it takes a couple of seconds, and then you might have some problems. But that's why I'm giving you a job, so you can control the execution. And finally, if you have subscribed to something, you also get a job from that coroutine, and you can stop it just by calling cancel. So if you want to stop listening, you just call cancel on that job. Same for the errors. And then also, if you have a custom dispatcher, it's a good idea to call close on it. For example, if you create a single-threaded dispatcher to have only one thread to consume your transitions in an orderly manner, then it's a good idea to call close on it, because then it would also stop the thread that is running behind it. So closing is smart. And then finally, when you're done with the state machine, you just call finish, and it cancels everything inside. It cancels the state flow. It cancels the coroutines that were created by the state flow for transitions. It cancels coroutines created by the state flow for errors. It cancels all side jobs that are internally in some kind of hierarchy with different coroutines. So it cancels everything and moves the state machine into a state of death. And if you call something on it, it explodes. That's the finish function, and it's actually the last function of the talk as well. So the talk is finished as well. I'm hoping that at least some of you got interested in the state flow and in the Kotlin coroutine framework, and maybe you would like to investigate, and maybe you would like to build something better than this, and we all be super happy to use it. So that was kind of my idea here, and I'm now happy to take any questions you might have, and obviously thank you all for coming.